Hello, today we're continuing in our series on particle physics, looking amongst other things at gauge theory, spontaneous symmetry breaking, and the Higgs mechanism. But first, a quick review. We've already learnt that there are four fundamental forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and the force of gravity. And we've learnt that three of these can be incorporated into a model on particle physics. At the moment, we cannot get gravity into that model, and in that respect, it's not complete. But let's look at those three forces. We'll start with the electromagnetic force because in some ways that's simplest. What the electromagnetic force does is it essentially is the force that operates between two charged particles. So if, for example, we take two electrons, which are like charges, and therefore they will repel because like charges repel, it means that if you bring two electrons together, they will push one another apart. But the question is, since they don't actually have to be touching, how does this electron know that this electron is here in order to push it away? And what we've discovered is that the reason that the force exists is because of virtual photons, which are called gauge bosons, or if you like, exchange particles, which are virtual because they do not exist forever. They come into being and then they go out of being, but they travel between these two charges and they communicate the force. So the force communicator, or the exchange particle, or the gauge boson, whatever you want to call it, in this case is a virtual photon. Photons are, of course, massless, and that whole principle is called quantum electrodynamics. And you'll recall that that was represented in mathematical form by the unitary matrix, one-dimensional U1. Then we looked at the weak nuclear force. Now this is a force which, amongst other things, is responsible for changing the flavour of quarks. So, for example, you can take a down quark and convert it into an up quark. Ups and downs are what are called flavours, by the emission of a W minus boson. So in this case, it's the W minus, which is the exchange particle or the gauge boson, that is equivalent to the virtual photon in the case of the electromagnetic force. But the W minus doesn't last very long before it decays into an electron and an anti-electron neutrino. The W minus is 80 times heavier than the neutron from which it was formed. This typically, you don't have individual quarks. This will typically be a neutron which consists of three quarks. So that will be an up, down, down neutron, because a neutron has two downs and one up. And then two of the particles, two of the quarks don't change, they stay as they are. But one of the down quarks changes into an up quark. So now you have up, down, up, and that of course is a proton. And so what you've got is a neutron converting to a proton by virtue of the fact that one of the quarks in the neutron, specifically the down quark, converts into an up quark by the emission of the W minus. But as I was saying, the W minus is 80 times heavier than the neutron from which it comes. A neutron is approximately 1 GeV, a W minus is approximately 80 GeV. So the question is, how can something that weighs 1 GeV, as it were, produce a particle that is 80 times more massive? And the answer is that we have to resort to that other version of Heisenberg's uncertainty principle, which says that delta E delta T must be less than h bar. That is to say that the amount of energy that essentially you borrow from the vacuum multiplied by the amount of time you borrow it for must be less than Planck's constant, which is a very small number. So this is saying that you can borrow energy from the vacuum, provided A, you pay it back, and B, you don't keep it for very long. And the more energy you borrow, the less time you can borrow it for. So we're borrowing a lot of energy from the vacuum here, 80 GeV, so that has to be paid back very quickly, in fact in 10 to the minus 25 seconds. So the W minus doesn't last for more than 10 to the minus 25 seconds before it decays into these long-term particles. In 10 to the minus 25 seconds, a W minus will barely be able to cross a part of a proton. That's as far as it will get before it decays. And that's why the weak nuclear force is a very short-range force, because the W minus, which is the exchange boson, only lasts for 10 to the minus 25 seconds and can't get very far in that time. This whole process is called quantum flavor dynamics, QFD, and in mathematical terms it's represented by the special unitary matrix SU2. Two-dimensional because you're changing from downs to ups, or as we shall see in a moment, you can change from ups to downs. Let's just look at this process of the down changing to the up via the emission of a W minus particle in a little bit more detail. We could represent that as saying that you start with a down, which stays down, and then you have an up, anti-up creation out of nothing. So out of the vacuum you get a particle, antiparticle creation. And what that appears to look like is that the down particle has changed into an up particle via the emission of a down anti-up. And that down anti-up, of course, is essentially the W minus boson. Free neutrons, that is neutrons which are not part of a nucleus, will convert to protons about every 15 to 20 minutes. So if you have a free neutron, it is not a stable particle. It will convert and become a proton. Protons we think are stable, or if they are not, they have got half-lives of very much greater than the entire age of the universe. But neutrons, unless they are in the nucleus, in which case for various reasons they are held in stability, if they are just free, they will change to protons by this process. And the fact that it takes 15 to 20 minutes to do so shows how weak the force is. It shows why if this W minus were massless like the photon, this process would happen almost spontaneously and neutrons would just decay into protons instantly. But because it's a weak force, and it's a weak force because you've got to borrow the energy from the vacuum to create the W minus, it takes time for neutrons to decay. Now I mentioned that it's also possible for protons to decay into neutrons, and the way that works is that you've got one of the quarks in the proton, which is an up quark, changing into a down quark by virtue of the emission of now a W plus. And that will quickly decay into a positron, which of course we'll find in the electron and annihilate, and an electron neutrino, not an anti-electron neutrino now, because the antiparticle is the positron. And of course there are two other quarks which do not change, so there'll be an up and a down, an up and a down. And so one of the quarks, the up quark, that's this one here, changes into a down quark, and so you've got an up, down, up, which is a proton, changing into an up, down, down, which is a neutron, by virtue of the W plus. Now, I said to you that protons do not generally decay into neutrons. So why is that? And the answer is that in this case, the neutron can decay into the proton because the neutron has a marginally greater mass than the proton. So since E equals mc squared, some of that mass can be converted into energy. So the neutron can decay into a slightly smaller mass proton, and the energy that's left, it doesn't of course create the W minus because there's not enough. That comes from the vacuum and has to be paid back by this formula. But the excess mass of neutron over proton is what can create the electron and the anti-neutrino. But when we come to this process, ordinarily this can't occur because the proton has less mass than the neutron, so you can't create a long-term particle when you've got less mass because there's no spare energy to create these additional particles here. So this arrangement can only occur in circumstances where you've got a huge amount of energy already available to you, for example, in the sun. And that's exactly what happens in the sun. The sun is just a huge ball of hydrogen. The electrons have been stripped off the hydrogen because it's so much energy there. So the hydrogen is ionized. Hydrogen without its electron is just a proton. So essentially the sun is just a massive ball of protons. And what is happening is that some energy is available to enable protons to convert to neutrons. And then you can take 2 protons and 2 neutrons and bring them together and form what is essentially an alpha particle, the nucleus of helium, and ultimately that's all the sun is doing. And it takes 10 billion years for the sun to do that. It's been going for 5 billion, it's still got 5 billion to go. And the reason that it takes 10 billion years is because the W plus particle is so massive at 80 GeV. And because it's so massive, it has to borrow energy from the vacuum in order to create the W+, which lasts for about 10 to the minus 15 seconds before it decays. If the W+ were massless, like the photon, this process would happen almost instantaneously. The sun would burn out in about a few million years, if that. And so there would never be any prospect of life forming because there just wouldn't be long enough for it to do so. So it's actually the reason we are alive is because the W plus has 80 GeV of mass. That makes this process weak. In other words, it rarely happens. So protons do not spontaneously decay into neutrons. Even in the sun, it takes a while. Think about it. There are protons in the sun that have been there for 5 billion years and they still haven't converted into neutrons. And there are some that won't even for another 5 billion years. So it's the weak nuclear force, the SU2, that causes the sun to shine. Finally, let's look at the strong nuclear force. In the case of the strong nuclear force, this is where the colours of the quark, remember they aren't coloured at all, this is just a way of labelling them, but where, for example, a red quark, this is a red quark, meets up with the position where you get a blue anti-blue creation out of nothing. This is just matter-antimatter creation from nothing. And so what appears to happen is that a red quark converts into a blue quark via the emission of a red anti-blue particle, and that particle is called a gluon. And that is called quantum chromodynamics. And because there are 3 colours of quarks, red, green and blue, you need a 3 by 3 matrix, and that's the special unitary matrix 3. And that's what's happening in the middle of the nucleus. That's what holds the protons and neutrons together. It's also what holds the quarks together within the proton and the neutron. And look, you can see the way that works. You could draw a Feynman diagram whereby you have a red anti-red combination. Here's a red anti-red. The two come together and annihilate here. And you can have a blue, take that blue through the red there, you can have a blue anti-blue creation. And so what this looks like is that a red quark has converted to a blue quark and a red bar quark has changed to a blue bar quark via the exchange of a red anti-blue gluon. And it's that combination of gluon exchange that goes on in the sun, which is essentially the exchange particle. The gluon is the exchange particle that creates the force, the strong nuclear force, that holds both the nucleus and indeed the nucleons together. Now I just want to think about gauge theory, or sometimes gauge symmetry, and this is very simplistic. Basically, you could think of gauge as meaning the same as coordinate. And in order for gauge theory to work, you need what's called gauge invariance, or in my terms, you could call it coordinate invariance. Imagine that this is the surface of the Earth, and that there is a region above the surface of the Earth, let's say the first 30 meters or so, where the gravitational acceleration can be regarded as pretty much constant. If I were to say to you, what is the potential at that point? What is the gravitational potential at that point? You couldn't actually tell me, because you don't know where my coordinate system is. You might think that I mean, what is the potential with respect to the surface of the Earth? And if that is true, you could tell me. But I might mean, what is the potential with respect to the top of a table? In which case it would be different. What I have done is to change my coordinate frame from one where the frame of reference has 0 at the surface of the Earth to one where the coordinate frame has 0 at the surface of the table. And so the change of coordinate frame, or if you like the change of gauge, changes what you would say that that potential was. But if I asked you what was the potential difference between 2 points, the gravitational potential difference between 2 points, now you can tell me, and that potential difference is entirely independent of where I set the coordinate frames. It doesn't matter. You could do the same sort of thing with a wire, and I could say to you, here is a wire, what is the electric potential at the end of that wire? You wouldn't know, unless I gave you 2 wires and asked you to measure the potential difference between the 2. And then it wouldn't frankly matter if one wire was at 9 volts and the other was at 0 volts, or one was at 109 volts and the other was at 100 volts. Either way, you're still going to measure a potential difference of 9 volts. So, although it's a good deal more complicated than this, when we talk about gauge invariance, what we're actually talking about is a system whereby what you're measuring is independent of the frame of reference that you're using to measure it. So since the mathematics of the weak and the strong forces, the SU2 and SU3, involve transformations. In the case of SU2, it's a flavour transformation from up to down or down to up. In the case of SU3, it's a colour transformation, red to green to blue. Those transformations must be independent of the frame of reference that you're using to measure them. What about spontaneous symmetry breaking? Well, again, a very simple example is to consider water. Imagine that you are a molecule of water in a bowl of water, and you look all around you, and what do you see? Symmetry. Everywhere you look, there are water molecules, H2O. They are all lined up in some orderly form. In every direction, you have got complete symmetry. Now let us cool that water to 0 degrees centigrade and below. Depending on the circumstances pertaining at the time, as I cool that water, I might get ice. I might get snow. I might get frost. And I might get ream, which is a kind of fog frost or a frozen frost. You could say that what you've got here is spontaneous symmetry breaking. Something which was the same has now changed into something which is completely different. And if you look at things like, for example, the snow crystal, which I can't draw very well, but it has that kind of hexagonal shape to it. That, in a sense, is symmetric, but only if you rotate it every 60 degrees. If you rotate that shape by 30 degrees, it wouldn't be symmetric anymore, certainly not symmetric with the original form. It wouldn't be gauge invariant in that sense. But in a sense, what we're saying is that you start with something that is exactly the same, and you end up with things that are, or appear to be, completely different. And that, in essence, is the argument about how the forces were formed. The argument goes like this. At the time of the Big Bang, which was about 13.7 billion years ago, there was a single force. There was energy, but in a sense it's rather like the water. Everything is the same. There is energy, there is, as it were, one force. But at the time of the Big Bang, huge energy equals temperature, so massive temperature, and then things begin to cool. And when you get to some ridiculously small time, which is 10 to the minus 46 of a second, different books will give you slightly different times, but the idea is that one of the forces separates out. That's the force of gravity. That's the one that we do not yet include in the particle physics theory of all the forces. And then after 10 to the minus 36 seconds, so still ridiculously small, the gravity is there, but now another force falls out, and that's the strong nuclear force. And then between 10 to the minus 36 seconds and 10 to the minus 32 seconds, you get what's called a period of massive inflation. No one's quite sure why, or indeed even if it happened, but generally that's the thinking, that the universe suddenly expanded dramatically. Now remember, this is only 10 to the minus 32 of a second after the Big Bang, so what we're really talking about is a universe expanding from the size of a proton to the size of an orange. You know, we're not talking massive at this stage, but nonetheless, that expansion in that amount of time is huge. And then the pattern goes on that at 10 to the minus 12 seconds, gravity is still there, the strong nuclear force, of course, is still there, but now the other two forces separate out to become the weak nuclear force and the electromagnetic force. And so from a single force, the argument is that within 10 to the minus 12 of a second, 1 millionth of a second, all the four separate forces have fallen out and are quite different. If we just complete the picture, by 10 to the minus 6 seconds, which is 1 millionth of a second, you get what's called quark confinement, which I'll come on to in a moment, which basically means quarks can never live by themselves again. They always bundle together in 2s or 3s. Within 3 to 20 minutes, you have the basis of nuclei. In other words, protons and neutrons are coming together really only to form things like the hydrogen nuclei, the deuterium nuclei, and the helium nuclei. That's basically all you'd get. But it would take another 380,000 years before you got atoms. And the reason for that is, of course, that atoms have to get electrons to orbit the nuclei, and you can take electrons out of atoms, you can essentially ionize the atoms if you give them enough energy. And the problem is there's too much energy going around for the electrons to be captured by nuclei. They can easily be ionized. So all the electrons are free until 380,000 years after the Big Bang, at which point the temperature has cooled sufficiently that the nuclei can start getting the electrons bound to them and forming atoms of hydrogen and helium. So the argument goes that from a single force, four separate forces have fallen out. Let's look at those forces and just compare them. First of all, we'll take the strong nuclear force, which will give a relative strength of 1, just so we can compare all the others. That operates, of course, only within the nucleus, so 10 to the minus 15 meters, and the force carrier, or the gauge boson, is the gluon. The electromagnetic force is the next strongest, but by comparison with the strong nuclear force, it's about only 1% of its strength. Specifically 1/137. 137 is the fine structure constant. The range of that force is infinite because it's a 1/r² force. As the distance increases, the strength of the force decreases, but it never reaches 0. And the gauge boson, or the exchange particle for the electromagnetic force, is the photon. Next we have the weak nuclear force, and the relative strength compared to the strong nuclear force is about 10 to the minus 6. As we said before, this has a range which barely gets it across a proton, let alone the nucleus, 10 to the minus 18 meters, because the W boson lasts for only 10 to the minus 25 seconds. So its range is very, very short. And the bosons are the W minus, the W plus, and a boson we haven't come across yet, the Z. The W minus is the gauge boson that carries away a negative charge. The W plus is the gauge boson that carries away a positive charge. The Z is neutral, so you have a Z gauge boson wherever you have neutral particles interacting, and that would, for example, be the neutral neutrinos. And then finally we have gravity, whose strength is about 10 to the minus 38, that of the strong nuclear force. It's pathetic by comparison, but like the electromagnetic force, it has an infinite range because it's a 1 over r squared, and nobody knows whether or if it has an exchange particle, but if it has, then that particle would be called the graviton. But I put it in brackets because A, we don't know whether it exists, and even if it does exist, we've never found it. So if you look at this, you'll find that there are hugely different strengths of these forces and hugely different ranges for these forces. Well, in fact, there's two that have an infinite range and two that have ranges within the size of a nucleus. And yet we are asserting that all of them fall out of a single force. So how can that be? Hold that thought and we'll come back to that a little later. But first, I just want to bring to your attention an experimental fact when we are talking about quantum flavor dynamics, that is where quarks change their flavor. So I'm going to redraw the diagram where the down quark changes to an up quark. Typically, of course, this is where a neutron changes to a proton. So you would have an up-down and an up-down, and those two quarks, the up and the down, don't change. But the third down quark changes to an up quark. So this is a neutron which changes to a proton. And it does it by the emission of the W minus gauge boson, which of course lasts for a mere 10 to the minus 25 seconds before it decays into an electron and an anti-electron neutrino. We drew that diagram earlier in this presentation. But here is the important point. And before I tell you it, let me just explain what I mean. If you remember our quantum mechanics concepts, we considered a thing called electron spin. Let's suppose the electron is travelling in this direction, shown by the arrow. I can measure the spin of the electron in any axis or any direction I like. I choose to measure it along the direction of travel of the electron. And we know that when you measure the spin of an electron, you can only get one of two answers. You will either get up or down with respect to the coordinate you choose to measure along. So in this case, up will be in the direction of travel and down will be contrary to the direction of travel. And what we mean by up or down is essentially the direction of the axis, and consequently the spin is around that axis. So if we are measuring an up spin, that means that if we're viewing from here, that means that the electron will be appearing to spin clockwise, or we could call that a right-handed spin. On the other hand, if we're viewing from here an electron whose spin is down, then that will appear to be anti-clockwise or counterclockwise, and we could call that left-handed. So in a sense, all you're doing is calling right-handed or left-handed whether or not the spin is measured as up in the direction of travel or down in the direction of travel. And what we find experimentally, so this is an experimental fact, when the down quark changes to an up quark by the emission of a W- boson, which then decays into an electron and an anti-electron neutrino, the electron is always a left-handed electron. You never get a right-handed electron. What is actually happening in terms of charge in this diagram is that the W- is carrying away a negative charge from what was a neutral particle, the neutron. And if it carries away a negative charge, then for charge conservation, it must leave a positive charge, which is why the proton has a positive charge. Similarly, when the W- decays, for charge conservation purposes, it must bestow its charge onto one of these particles. Of course, it bestows its charge onto the electron. But what you could consider, this is a way of looking at it, is that for the purposes of the weak nuclear force, not for the purposes of just general electromagnetism, of course, because right-handed and left-handed electrons are, of course, both charged. Electrons are charged particles, you can't get away from that. But for the purposes of the weak nuclear force, which is what we're talking about here, you could argue that the W- can only bestow its negative charge on the left-handed electron because for the purposes of the weak nuclear force, only a left-hand electron has a charge, a right-hand electron does not. Now I repeat, of course electrons, whichever way you measure them, for the purposes of the electromagnetic force, have charges. But what you could consider, the way you can think about this is that the W- bestows its charge on the left-handed electron because for the purposes of this particular weak nuclear force, the right-handed electron cannot accommodate a negative charge. That's the sort of way to think about it. But we know that right-handed electrons can change into left-handed electrons and vice versa. We know that for at least two reasons. The first one is this diagram I've just drawn you here. And let me just redraw it. Let's say this is the direction of travel. And let's say that I'm viewing the electron from here. And let's say that I do indeed measure a left-hand electron, which means that the spin is counterclockwise as viewed from here. Now, electrons do not travel at the speed of light, so it's theoretically possible that I could run along and get in front of the electron and then view it from here. The electron hasn't changed, it's still spinning in exactly the way it was before, but from my new perspective, I will see that an electron that was spinning counterclockwise, I'll say that again, was spinning counterclockwise when viewed from here, will now appear to be spinning clockwise when viewed from here. Try it yourself. If you simply turn something in a direction that's anti-clockwise when you're behind it, so this is anti-clockwise, if you now look in front of it, you will see that that actually appears to be clockwise. So in other words, the left-hand spin electron viewed from here has become a right-hand spin electron when viewed from here. It hasn't changed at all, it's just the gauge, if you like, or the way I've looked at it has changed. So I can actually see a right-hand electron simply by overtaking it and looking at it the other way. But we also know that you can get electrons that change from left to right from the Dirac equations, which we derived in an earlier video in this series. And let me just remind you what they were. We said that I d psi right by dt is equal to minus I alpha, where alpha, you may remember, was a matrix, d psi right by dx plus m psi left. And the reason it was psi left is that there was another matrix here which was beta, and what beta did was to act on essentially a combination of psi right and psi left to give you psi left. I refer you to the way we derived it earlier, so I don't have to redo it. There was another equivalent equation which said that I d psi left by dt is equal to minus I alpha d psi left by dx plus m, where m is the mass term, psi right. So essentially what you've got, since I could actually, if you like, I could take these terms over on the other side of the equation. So I cross out the equals and make those plus terms, and then I put the equal sign here. So all I've done is to move these terms on the other side of the equation. I've now got a psi right term plus a psi right term equals a psi left term, and a psi left term times a psi left, plus a psi left term is a psi right term. So this is a left converting to a right. That's a right converting to a left. This is a left converting to a right. So now we've got the Dirac equations showing us that you can change from lefts to rights. But I have just asserted, in a fairly hand-waving way, that somehow when you've got the weak nuclear interaction, the W minus can only bestow its charge on a left-handed electron, which means that for the weak nuclear force purposes, there is actually a difference. So when you've got a right-handed electron changing into a left-handed electron by virtue of these equations here, somehow you must have some other field, which I will call phi, which is, as it were, in this case, bestowing the charge on the left-hand electron, because we're saying that for the weak nuclear force, the right-hand electron doesn't carry charge, but the left hand does. Or similarly, if you want to draw the other diagram, when the left hand changes into a right hand, there is a kind of a opposite version of the field, which I describe as phi bar, which interacts in order to, as it were, absorb the left-handed charge and produce a chargeless right-hand electron. I say it again, this is for weak nuclear force purposes only, not in terms of electromagnetic. So we also said in particle physics that this is all really about quantum field theory. These particles are not really particles at all, they are excitations of fields. So actually these are fields which are interacting. The right-hand field interacts with another field, which I have called phi, to produce the left-hand field, and vice versa. What is this thing called phi? Well, of course, it's going to turn out to be the Higgs. So let's just draw the this thing called phi. Let's draw phi, and we'll consider, all fields have energy. Let's consider the potential energy stored up in this field called phi, and let's suppose that it has a pattern that looks like this, which is something you might think to be the case. When the field has a value of 0, the energy has a value of 0. But as the field increases, so the energy increases. Now that you might think is a perfectly reasonable pattern. If there were such a field, then of course the lowest energy state, where would you sit in order to minimize your energy? The answer would be at a point at which the field phi had a value of 0. And if the field phi has a value of 0, it isn't going to do much good when you interact it with left and right-handed electrons, because it's not going to have any value, because its value is 0, to have any effect. But suppose that the diagram instead, this is still potential energy against, that should be phi, not Q, against the field. Suppose it looks something like this, which is going to be in 3 dimensions. So this is, you can consider this, as some people do, as a Mexican hat, or in some cases a wine bottle, the bottom of a wine bottle, where the bottom is indented like this in order that the sediment can accrue in the ditch, as it were, or the trough that is a 3-dimensional trough around the base of the wine bottle. You could consider, of course, if you took, let's say this is a wine bottle, I could think about balancing a marble on the top of the inverted part of the bottom of the bottle. And if I was very, very careful, I could just about get an equilibrium, and that would be perfectly symmetric. But it would be inherently unstable, because I've only just got to knock that bottle a little and the marble will roll down into one of the troughs. Now, which way will it roll down? We have no idea. It will roll down into a trough somewhere around this base. And then it will be stable. Once it's rolled down, let's say to here, it's stable. It is at its lowest potential energy. But the field now has a value. Instead of being 0, the field has a value and therefore can interact with the fields of these other particles. Now, let's take this marble analogy a little bit further. We can't go too far with this because it doesn't quite work, but for introductory purposes, I think this is okay. This marble can do two things in terms of movement. Firstly, it can just roll around the trough at the bottom of the bottle. And when it rolls around the trough, it is staying at potential energy equals 0. So no energy is required to roll around the bottom. And that was called the Goldstone boson. It's a massless particle because it has it requires no energy. The other thing the marble can do is to oscillate up and down these walls. So it can kind of, oscillate around, not around the trough, but as it were up and down the sides. That, of course, does take energy. In fact, it takes quite a lot of energy because these are very steep sides. And when it oscillates, that is called the Higgs boson. And it's the Higgs boson that is effectively the exchange particle that gives certain of the fundamental particles their mass. And I've done a separate video on the Higgs, which you'll find in the playlist on particle physics. And you may want to stop and look at that now. So now let's get back to that question of what makes the four forces significantly different when we are asserting that they all came from the same basic force at the time of the Big Bang. Well, let's consider first of all gravity and electromagnetic forces. Those are the two that are infinite in range. And we could, as it were, have an analogy of a light beam. A light beam's intensity falls off as 1 over r squared. In other words, the further you go away, the intensity falls off 1 over r squared. In exactly the same way that the gravitational force and the electromagnetic force fall off on a 1 over r squared term. They are infinite because no matter how far you go away, no matter how large r is, 1 over r squared never gets to 0. So using this analogy, what could we do to create a situation where that light beam had a very, very small range? Well, the answer is we could confine it. We could put it in a box. And if we put it in a box, now the light has a very narrow range, the range of the box. It can't get out, as long as the box is not transparent, but if it's a cardboard box, you can't see the light anymore. That's called confinement. And that, in essence, is what happens for the strong nuclear force. The force is confined within the nucleus. The other thing you could do with this light, in order to stop it from having an infinite range, is to surround it by a bit of fog. Now here you'll have to work with me on the analogy because fog doesn't quite work like this. Fog tends to reflect light or cause it to scatter. I want you to imagine that there's a fog around this light which absorbs the energy and thus prevents it from travelling very far. So that is, in a sense, what is happening with the weak nuclear force. That the whole energy is just absorbed before you can get very far. And so here are ways in which, analogies in which you can imagine you've got the same force. For two of them, you've got an infinite range. For the other two, there are mechanisms which happened when the spontaneous symmetry breaking took place, which effectively reduced, as it happens, extremely reduced, the range of those forces by virtue of confinement or absorption. How does quark confinement actually work? Well, let's take a particle. It could be a neutron, it could be a proton. It consists of 3 quarks. And the reason I've drawn it like this is we're going to have some kind of experiment which is going to attempt to separate out one of the quarks. So we've got to essentially find some experimental mechanism of pulling one quark away from the other 2, in the hope that we can then break the bond, and we are then going to have what we want, which is an isolated quark. Now it turns out that what happens is, as you try to do this, as you pull this quark further away from these 2, the energy between the 2 parts increases. And it just keeps on increasing the further you pull these quarks apart. So if you have, for example, a proton, which of course is 2 ups and a down, what you would find is that you get this kind of tube of energy as you try and pull one quark out, until there is so much energy that in fact what you get is particle creation. And of course you always get matter and antimatter created whenever you have this particle creation from a high energy. So we've got a huge amount of energy, so much so that there's enough energy for particle creation, and you get an up-anti-up quark pair formed. And then what happens is this up particle goes here, and the up bar, or the anti-up particle, goes here. And so all that happens is you get an up-up-down, which is the proton you essentially started with. But over here, instead of getting a single quark, you now get a meson, which is an up-anti-up. That, of course, is just an ordinary pion. So you never get a quark on its own, because before you can get to a quark on its own, there will be so much energy that there will be pair production, and the pair production will just leave you with the proton you started with plus a meson. That's called quark confinement. You can never, ever get one quark separate from all the others. Okay then, so now I want to look at the question of how it is that these 4 forces have such significantly different strengths, from the strong nuclear force, which we weighted as 1, to gravity, which was 10 to the minus 38, the size of the strong nuclear force. So let's just think about what those forces actually are. For the electromagnetic force, that we know is Coulomb's law, which is just Q1, Q2, that is the charge on 2 particles multiplied together, divided by 4 pi epsilon naught r squared, where r is the difference between them. The distance between them. And I can rewrite that, if I like, as k Q1, Q2 over r squared, where k is just 1 over 4 pi epsilon naught. What is the gravitational force? This is, of course, Newtonian. This will simply be g, the gravitational constant, times the first mass times the second mass, divided by r squared, where r is the distance between them. So now let's think of 2 electrons. Of course, the electrons will have a charge of E, the electronic charge on the electron, and they will have the mass of an electron. So now I can write that the electromagnetic force of 2 electrons will be equal to K, and Q1 and Q2 are both E, the charge on the electron. So that's Ke squared divided by r squared. So that's the electromagnetic force between 2 electrons. What is the gravitational force between 2 electrons? Well, that will equal G. And now M1 and M2 are both the mass of the electron, which we'll call M. So that's M squared over R squared. At this point, I just need to remind you of some of Einstein's formulae. We know that the momentum is equal to h over lambda. That is to say, the momentum of a particle, whether it's a photon or, as Louis de Broglie pointed out, an electron, the momentum is Planck's constant divided by the wavelength of the wave associated with that particle. And we can kind of think of that as h over r. In other words, if the distance between the two particles is of the order of its wavelength, so they are very close together, then we're going to say that the momentum is h over r. We're also going to recall that E equals pc, which is equal to, since p is h over r, hc over r. Then Einstein's famous formula E equals mc squared, which means that m is equal to E over c squared, and since E is hc over r, that is hc over r c squared, because hc over r is E, and then you've got a c squared here, and that is equal to h over rc. So what we're saying is that the mass of, let's say, the electron is equal to E over c squared, which is h over rc, because we got that from here. So what I'm now going to do is to take this m term, the mass of the electron, which I'm now asserting is h over rc, and I'm going to stick that into this equation here. So now Fg, which the gravitational force between the two electrons, which remember we said was gm squared over r squared, that's just to remind you here. Now I'm going to say that m is h over rc, so that is going to be g over r squared times m squared, which is just going to be h squared over r squared c squared, and that's gh squared divided by r to the fourth c squared. So now I've got a force which is now expressed in these terms. This is a c, the speed of light. So now I'm ready to say, what happens, is there a possibility that those two forces, the electromagnetic force, ke squared over r squared, could be equal to the gravitational force? Well, let's set them equal. The electromagnetic force is ke squared over r squared, and that I'm going to say is going to be equal to the gravitational force, which is gh squared over r to the fourth c squared. And if you work that out, what you should find is that the r to the fourth cancels the r squared to give you an r squared term here, and that is gh squared over ke squared c squared. In other words, when r squared has this value, which you'll notice is all constants, all of these terms are constant, when r squared has this value, the gravitational force between the electrons is equal to the electromagnetic force between the electrons. So let's just get an idea of the order of magnitude. I don't want to do this too precisely because it doesn't quite work like this, but it'll just give you a flavour. Forget the numbers associated with it. G is 10 to the minus 11. It's actually 6 times 10 to the minus 11, but let's forget about that. H squared, well, H is 6 times 10 to the minus 34. 10 to the minus 34 squared is 10 to the minus 68. K, I can tell you, is actually 10 to the 10. That is 1 over 4 pi epsilon naught. E squared, well, that's the charge on the electron squared. That's 1.6 times 10 to the minus 19. We'll call that 10 to the minus 38. C squared is, of course, the speed of light squared. Well, that's 3 times 10 to the 8. We'll call that 10 to the 16. You can do this more precisely if you want. So on the top, we've got 10 to the minus 79. And on the bottom, we've got 10 to the minus 12. And that of course is going to become 10 to the minus 67. And that of course is r squared, which means that r is, to all intents and purposes, 10 to the minus 33 meters. So when 2 electrons are 10 to the minus 33 meters, which is of course amazingly absurd small distance. When they are that separated, the gravitational force and the electromagnetic force are the same. And of course, when you talk about the Big Bang, you're talking about something that grew from essentially what we call a singularity. So actually everything would be at that distance, at a minute time after the Big Bang. And all the forces could therefore be the same if you use the same kind of analogy. We've got the gravitational and the electromagnetic force being the same if they are this distance apart. Well, remembering that r is 10 to the minus 33 meters, let's consider what the energy would have to be in order for that to be the case. So just a reminder that E equals PC, which equals hc over r, because we said that P is h over lambda, but when lambda is of the order of r, we can call this h over r. And what is that going to be in numbers? Well, again, we're just doing a hand waving exercise. H is 10 to the minus 34. C is 3 times 10 to the 8, so we'll call that 10 to the 8. And R, we said, was 10 to the minus 33. And that comes to 10 to the 7, and that's energy, and energy is measured in joules. To convert joules to electron volts, you essentially have to multiply by, multiply by 10 to the 19. So 10 to the 7 times 10 to the 19 is now in electron volts. So that's essentially 10 to the 26 eV. And that is the equivalent of 10 to the 17 GeV. So when the energy was 10 to the 17 GeV, the electrons would have been 10 to the minus 33 meters apart, and the strength of the forces would be the same. Now, if I tell you that the Large Hadron Collider, when it's working at its peak, will have something of the order of 10 to the 4 GeV, you can see that it's a long way short of the 10 to the 17 GeV that I have calculated, which would be the conditions fractionally after the Big Bang. In fact, if you do the calculations, you often find that the energy is calculated at more like 10 to the 15 GeV, but look, you know, what's a couple of orders of magnitude between friends? So the argument is that if you stretch back over time, this is time, this is strength of forces. At the moment, you've got the strong nuclear force, the electromagnetic force, I'm not drawing this to scale, the weak nuclear force and the gravitational force, which are all entirely different strengths. In fact, gravity is 10 to the minus 38, the size of the strong nuclear force. But the argument is that if you plot those back to the time of the Big Bang, what you find is that at that point, they all had the same strength, but the energy at that time was about 10 to the 15 GeV. I calculated it as 10 to the 17, but hey, never mind. So that's the thinking, that they all had the same strength when they were at incredibly high energy, where the particles were incredibly close together, but that spontaneous symmetry breaking has led to a situation where it looks as though we've got 4 completely different types of forces. But in fact, the assertion is that they all stem from the same.